el fuego que arde tu piel. Soy el agua que mata tu sed. El castillo, la torre, yo soy la espada que guarda el caudal. Tú el aire que respiro yo y la luz de la luna en el mar. La garganta que ansío mojar, que temo ahogar de amor. Y cuáles deseos me vas a dar. Oh, dices tú, mi tesoro, basta con mirarlo y tuyo será.
So today, our group will be presenting on what evolutionary stressors could have caused new strains and new variants of concern to arise in different geographical regions. We observed that without a treatment for COVID-19, new strains of the virus were still evolving in various geographical regions around the globe, and without a treatment to cause selective pressure and natural selection on the virus's evolution, we hypothesized that the virus's regional evolution arose from genetic drift as a result of geographical isolation, and that selective pressure within the isolated geographic areas caused a rise in variants of concern. So I want to begin by providing some background on geographic isolation and the effects of it. So geographic isolation is a term that refers to a population of animals, plants, or other organisms that are separated from exchanging genetic material with other organisms of the same species, and it is known to contribute to divergent evolution resulting in unique phenotypes. So how does this all relate to COVID-19? As we all know, COVID-19 originated in Wuhan, the capital of the Hubei province in the People's Republic of China. However, due to global travel and the high transmissibility of the virus, it quickly spread internationally. As documented by the WHO timeline, SARS-CoV-2 spread first to surrounding countries like Japan and Thailand within the Southeast Asia region by mid-January. It then continued out to the United Arab Emirates by January 30th, and 2 cases were documented in the African region and several in the Western Hemisphere by mid-February. By March 13th, the Director General said that Europe had actually become the epicenter of the pandemic, with more reported cases and deaths than the rest of the world combined, apart from the People's Republic of China. On April 4th, over 1 million cases of COVID had been confirmed worldwide, a more than 10-fold increase in less than a month. So as we all know, travel bans began as early as January 23, 2020, in order to decrease international and regional transmissibility of the virus. However, my group was interested in seeing how these travel restrictions, or in other words, government-imposed geographic isolation, could have affected evolution of the virus into regular variants and variants of concern. So one study published in Nature in August 2020 performed a phylogenomic analysis of 3 superclades, which were isolated from the outbreaks of distinct geographic regions, China, USA, and Europe, within SARS-CoV-2. And what they found was that there was actually little evidence of local or regional adaptation, suggesting instead that viral evolution is mainly driven by genetic drift and founder events. Therefore, genetic differences among SARS-CoV-2 strains sampled from these diverse locations could therefore be linked with their geographical distributions. Additionally, the WHO published a report in 2014 documenting the effect of travel restrictions on the influenza epidemic of 2009, and what I found in this report was very interesting. Although travel restrictions would reduce the spread to new cities, it also increased the risk of large, localized outbreaks with higher rates of mortality in some regions. And although this extends outside the scope of the WHO report on influenza, it got me wondering whether geographic isolation could also be causing variants of concern, or variants with a higher rate of spread and mortality that we are seeing pop up in different regions now. Of course, this will require much more study to prove, but the findings do seem to point in that direction as of now. So we are aware of the fact that geographic isolation is not the only selective pressure causing evolution of the virus. Therefore, Chris will now give a quick background on DNA, RNA viral evolution mechanisms to lead into T0rrent's analysis of other selective pressures that may have caused regional evolution of the virus.
Now, to give some quick background on viral evolutionary mechanisms. Much like eukaryotic evolution, viruses can evolve through single nucleotide polymorphisms. Single nucleotide changes and small insertions and deletions are extremely common. A key difference that makes viral evolution more rapid is that large-scale duplications and deletions can occur within a relatively small time frame without any loss of function. Additionally, viruses possess the ability to genetically recombine their genome by combining their DNA with a similar viral strain or a completely unique variant. Finally, viruses can enact horizontal gene transfer, exchanging codons with other viruses and in some cases host DNA. Longer sequence DNA viruses and RNA viruses can do this with greater speed, leading to many strains of the same virus. This is a huge reason why viruses like the common cold and HIV have never been cured.
What really are the possible causes of selective pressure on the evolution of SARS-CoV-2? Do we really have any ideas? Here are some. As we have learned during this semester, evolution is inevitable. Natural selection applies as much to SARS-CoV-2 as it does to any other organism. COVID has been reported to mutate less rapidly than flu or HIV, but some variants spread faster than the others, which means they have higher rates of infection. Between all three viruses, only SARS-CoV-2 has a proofreading mechanism, which results in a lower mutation rate. Now, normally, a typical COVID virus will accumulate 2 single-letter mutations per month. This is about half the accumulation rate as influenza and 1/4 that of HIV. Most of these mutations don't really affect viruses' ability to spread, cause the disease, or change levels of severity to a significant amount since the surface protein shape isn't really altered. As previously mentioned, there have been new variants of the coronavirus that have been popping up more frequently within a few months in the last year. For example, the UK variant, South African variant, and the Brazilian variant all started emerging around the same time in December of 2020. Why is that? So, some speculations. These variants might have emerged from lack of hosts or increased immunity in hosts. The COVID's rapid evolution may indicate increasing and persistent selection pressure being imposed onto the virus. So as degrees of immunity increases, meaning how well the host can protect itself against the virus, the COVID variant that's able to get past the body's defenses are favored and are able to propagate, leading to more of that variant. So, just to break it down a little further, selection can occur within an individual or within a population. In an individual, people with weak immune systems allow for viruses to mutate around and see what works to effectively counteract the body's immune defenses. That variant is favored. There's absolutely enough time for the virus to evolve. We have to consider the interaction between the pathogen and the host. The virus isn't going to kill the host right away. It'll take a sweet time to replicate and achieve that highest level of virulence and then spread from that host. From a study, they found that within the individual, there were variants that were found to show signs of adaptation to avoid antibodies in blood plasma treatment trials. Okay, now within a population, regions where people develop immunity after being exposed to COVID show strong selection pressure against the variant that they were exposed to. Well, and new variants have an advantage here. As you can see, in comparison to other viruses and diseases, research for COVID is still relatively new and studies are limited to information that we currently have. As time passes and as COVID continues to spread, more mutations and thus variants are more likely to pop up due to increasing selective pressure imposed onto the virus by our treatments. We're still in the early phase in seeing how the battle of vaccines and the virus plays out. In most viruses and bacteria, treatments and vaccines would typically lead to evolution of traits that would allow the population to survive and thrive and continue to spread. Some interesting research to conduct in the future could be exploring how COVID-19 will mutate in the future and how we might be able to predict and combat that. As research continues, I'm sure we'll be able to find more concrete answers to these questions. This could probably be the beginning of an arms race against the virus, and the more we are on top of it, the better we can be at identifying these changes and have it be useful in the development of future vaccines.
What a story, Mark.
Yeah, you can say that again.
What a story, Mark.